Hello everyone, welcome to Excel Engineering Education. In this video, we will discuss about stiffness matrix method for beam. Let us solve this problem, span ABC, which is a propped cantilever. Step 1, we want to identify the static indeterminacy of this particular beam and the redundant forces along this beam. So the static indeterminacy is nothing but unknown forces we want to find out. Here there are three unknown forces for fixed 1 and 2. So ultimately 5 unknowns, and we have equilibrium equations are 3. So by thumb rule, static indeterminacy is 2. Now we want to identify where are the unknown forces or the redundant forces. Let MA and MB, that is moment at A and moment at B, will be the unknown forces for this particular span ABC. Now, after these unknown forces, we want to find out the M upon EI diagram. Here, when we release this structure, it will be a simply supported beam. That's why we will find out the maximum bending moments along this particular separate span. So let us calculate the bending moment diagram for these particular span. We already know for portion AB, it will be a UDL. So bending moment will be nothing but WL square by 8. That is nothing but 60 into 4 square by 8 is equal to 120 kilonewton meter. And for portion BC, it is a centrally point load, that is WL by 4. So ultimately 100 into 3 divided by 4. So it answer comes 75 kilonewton meter. This is all about the moments. As we released it, it will be a simply supported and a separate. If you consider the beam, we will get a moment. Now after that, let us draw a bending moment diagram for this. So ultimately, this is your span AB, this is your span BC, and as it is UDL, it will be shown as a parabola having the value 120, and portion BC is nothing but a point load. It will be shown as a triangle having the value 75. So when we divide it by EI, it will be M upon EI diagram. Let us draw a conjugate beam for that. That is nothing but A dash, B dash for these two somewhat separately, and C dash. Now we want to find out a shear in this conjugate beam. So because this is important whenever we want to calculate a delta matrix. For that delta matrix, we want to calculate the shear along this particular beam. So in the conjugate beam, shear 1, that is the delta L1, is nothing but shear in this conjugate beam. The shear in this conjugate beam can be calculated with the help of our beam conjugate method. We already know the base for this is 4 meter and base for this is 3 meter. Let us calculate it. The shear in the conjugate beam, nothing but a force in this particular beam at A, is nothing but delta L1 is equal to 1/2 into area of this particular parabola is 2/3 of base. Base is 4 into height is 120 upon EI. So ultimately it will be 160 upon EI. This is shear along this particular A point. And then for delta L2, that is second value, it will be 1/2 area for this plus area for this particular triangle, that is 1/2 2/3 of base into height 120 upon EI plus 1 half. Half is what? At that particular reaction point. That is nothing but at A. At B there are 2. That's why we are adding 2. 1 half into triangle area, that is 1 half. Base is 3 into height is 75 upon EI. So when we solve it, delta L2 is equal to 216.25 upon EI. So here we will get a delta 1 and delta 2, and we want to write down into a matrix form. So our delta L matrix is equal to, first value is 160 upon EI, that is delta L1, and delta L2 is 216.25 upon EI. Now regarding the delta matrix, we don't have any external loads along these two directions, external moments or external load, additional loads. That's why delta matrix is 0. This delta matrix will be 0 0, as there are two redundant forces. Static indeterminacy is 2, so ultimately we will have 2 by 2 matrix itself. Now we want to calculate a flexibility matrix, which is called as a delta matrix. Whenever we want to do it, first we have to give a unit displacement along those coordinate direction. So first we'll give unit displacement in coordinate direction first. Whenever we will give a unit displacement in a coordinate direction 1, this beam can be written drawn as, again, redraw. This is our point A, this is our point B, that is something again BC, we consider it separately. So this is all about BC, and this is at A. When we will give a unit displacement at this B, that at this point A, so ultimately there will be the moment, because we are giving, there is a moment, we are giving the rotations, that's why it is 1. And whenever there is a moment at A about 1 kilonewton meter, then other will going to be like this. So this is all about 1 upon EI diagram, because we are giving moment at A, which is a 1 kilonewton meter. So this is all about our diagram. This is A dash, this is B dash, and this is C dash. Again, similarly, we want to find out here, whenever we want to find out it will be delta 1 1 and it will be delta 2 1, because it is 2 by 2 matrix and we want to find out a delta matrix. Therefore we will calculate now delta 1 1 and delta 2 1 for this conjugate beam, which is a simply supported beam. That's why delta 1 1 is equal to area of this triangle, ultimately 2/3 of 1 half into 1 upon EI into 4, that is 1 half base into height for this triangle, and this is 2/3, nothing but CG of this triangle. Ultimately, whenever we want to calculate it, let us remember that whenever we are calculating at A, multiply with 2/3, and whenever we are calculating at B, multiplied by with 1/3. So that same concept is here, and that we can do it. So ultimately this value comes to 4 by 3 EI. It is not like that we already done CG of this is at this point, because it is not exactly equilateral angle. So it will be here at delta 1 1 it will be 2/3, and delta 2 1 it will be 1/3. So this is all about 4 by 3 EI. The next is delta 2 1. Delta 2 1 is nothing but at this point. That's why it is 1/3, 1 half base into height 1 upon EI. That is something which I had written again here. So ultimately this comes to twice upon EI, thrice EI. So when we are calculating at delta 1 1, it will be 2/3 of base into height, and delta 2 1, it will be 1/3 of base into height. Kindly remember it whenever we are solving these kind of problems. So next we will give the unit displacement in the coordinate direction 2. Let us give the unit displacement in the coordinate direction second. Whenever we will give a unit displacement along the coordinate direction second, we will have this diagram, which is nothing but at B 1 upon EI, that is moment. Here for this particular beam, our span is 4 meter and 3 meter. So we'll write it first. This is 4 meter and this is 3 meter. Now when we will give a unit displacement of coordinate direction 2, it will be delta 2 2 and it will be delta 1 2. That is one which we want to find out. Here delta 1 1, so we already calculated, and delta 2 1 is also we calculated. Therefore delta 2 2 is equal to at 2. That's why for these two triangles at this particular point we want to calculate. It will be 2/3 now. Here 1/3, here will be 1/3, it will be 2/3 at this point. That will be 2/3 of 1/2 base for this first triangle, base into height, plus 2/3 of 1/2 base into height. Height is 1 upon EI. So when we calculate it, it will be 7/3 EI for this triangle first and then the second triangle. Kindly remember, whenever you are solving, at this point it will be 2/3 and at this point it will be 1/3, and delta 1 2 at this point it will be 1/3 of 1/2 base into height is 1 upon EI. So ultimately it goes to 2/3 of EI. So we calculated the values for delta 1 1, delta 1 2, delta 2 2 and delta 1 2. Here delta 1 2 and delta 2 1 is same. This is nothing but a delta matrix. Now we'll substitute all these values in this flexibility matrix. Here in the flexibility matrix, first is delta matrix. So delta matrix, that is nothing but 4 upon E thrice of EI, which we calculated already, then 2 upon thrice of EI, then again 2 upon thrice of EI, and the last is 7 upon thrice of EI. So this is all about delta matrix. Here we want to calculate these values, that is P1 and P2. We want to find out. These are the unknowns which we need to find out. So this is all about P1 and P2. Next is delta matrix. We don't have any external, that's why delta matrix is 0, and delta L, that is nothing but we already calculate 160 upon EI and 216.5 upon EI. Now we need to solve this equation, and whenever we want to solve, let us take a common 1 upon thrice of EI, then inside will be 4 2 2 7. We want to find out P1 and P2. These are the final values which we need. Then delta del minus, actually this is del minus delta L, or delta minus delta L matrix. So it will be, take common 1 upon EI, which will give us minus 160 and minus 216.5. This is delta minus delta L matrix. Okay. So now we want to find out P1 and P2. Here we can rearrange it, and it can be P1 P2 is equal to thrice EI will get cancelled. It will be thrice into 4 2 2 7, and we want inverse of it into minus 160 and minus 216.5. Now when we solve the inverse, we will get the final values. So let us calculate P1, P2 is equal to, inverse of it will be 3 into cross multiplication, that is nothing but 4 into 7 minus 2 into 2 into 7 minus 2 minus 2, 4, exchange the value, into minus 160 and minus 216.5. So when we solve it, we will get a value that is 1/8 of minus 687 and minus 546. So ultimately we will get a value of P1 and P2, that is nothing but minus 85.875 and minus 68.250. So this is all about the unknown values which we calculated. And the last step is nothing but step number 6, which is bending moment diagram. We want to calculate a bending moment diagram for this particular given beam. So this can be drawn as our span, this is a span A, and we given a coordinate direction 1 for this particular beam. Here is B and here we have C. So ultimately we had given a coordinate direction, sorry, which was already considered. It will be now in this direction and it will be in this direction, because direction will going to change, and these values are 68.250 and this is 85.87. So ultimately these are our values. Now we want to draw a bending moment diagram. Whenever we want to draw a bending moment diagram, let us draw a span as it is, which we already know some values, that is nothing but moment at AB. This is our A, I think this is our B, and this is C. So this is A, B and C. For AB, we already know the bending moment diagram which we calculated as a UDL, simply supported beam. It will be 120 and 75. This is all about 120 and this is 75. And for this, which we calculated already using our flexibility matrix, the moment is 85.87. Here the value is 68.250. Now after joining this point, that is from A to B and A to C, at C it is nothing but at the end which is a simply supported. That's why this value comes to 0, which completes our bending moment diagram and which completes the problem for flexibility matrix method for beam. Thank you for watching. Kindly like, share, subscribe. Excel Engineering Education.